the first thing that we're going to do today is involving the table that I gave you guys. So you should have had a table that was passed around the room and all that kind of stuff, and you'll notice that it is only partially filled out. And it is partially filled out by all of the Laplace transform pairs that we have already talked about, right? So when we introduced Laplace transform, I believe I explicitly found the Laplace transform of the unit step function, which we found to be 1 over s. Then I found the Laplace transform of e to the negative at times the unit step function, which we found to be 1 over s plus a. We used that relationship to find the Laplace transform of a cosine function multiplied by a unit step function, as well as a sine function multiplied by a unit step function. We put those two Laplace transforms together to find the Laplace transform of a cosine function that has a phase angle, as well as a sine function that has a phase angle. And then when we introduced the time shifting property in particular, or excuse me, the frequency shifting property in particular, we were able to derive the relationship for a cosine function that was multiplied by an exponential function and a sine function that was multiplied by an exponential function. So the first thing we're going to do today is we're going to run through a few more of these properties to kind of fill out this table. The ones towards the bottom, particularly number 15 and 16, are going to have to wait till later today or possibly on Monday's class meeting when we cover partial fraction expansion for complex roots and repeated complex roots in order to take care of those, because it just doesn't come out prettily using the Laplace transform properties. All right, so let's start with something fairly easy. Let's say, I don't like that color, that our function that we want to find the Laplace transform of is the Dirac delta function. Now, I'm bad at integrals, so I'm going to avoid using any type of integration or anything like that if at all possible. So very obviously, we could literally just use the definition of the Laplace transform to do everything we're going to do today, but I'm not going to do that. I'm going to use the various properties in order to figure out what these other identities are. Okay? So what do we know about the unit step function? The unit step function is the derivative of, excuse me, the Dirac delta function is the derivative of the unit step function, right? So I'm going to say that g of t is my unit step function, and therefore f of t represents the integral of g of t dt. Anybody have a problem with that? Exactly right. So the unit for a unit step function, the only transition it has is that t is equal to 0. So we have an impulse because it changes instantaneously from 0 to 1. So it blows up to the Dirac delta function blows up to infinity because the slope of that line is infinity at that point. And then everywhere else it has no slope, so its value is 0. So the derivative of a unit step function is indeed the Dirac delta function.
Right, that's what I said.
Yes. Oh, you're right. Sorry. That's on me. That's for, yeah, you're 100% right. I'm just being a jackass. Thank you for that, Ben. Okay, so we're going to be using the derivative relationship. Would help if I looked at my notes. So the Laplace transform of our Dirac delta function is going to be the Laplace transform of the time derivative of, and I don't need this dt here, sorry about that. G of t. So using our time differentiation property, this is going to look like s times g of s minus g at 0 minus. Right? What's the value of the delta function or the unit step function at t is equal to 0 minus? 0, because it's the instant before we triggered up, right? So this part is going to go to 0. Using our table, this is simply s times 1 over s. And so the Laplace transform of a Dirac delta function is simply the number 1. Okay. And no calculus involved whatsoever. We're simply using the results of our previous lectures in order to figure things out. Okay, so this one, fairly easy. What if our function were t times the unit step function? This is commonly known as a ramp function, linearly increasing as a function of t. How can we tie this thing back to stuff that we already know about? Well, I would argue, hopefully it's fairly obvious, that the ramp function is the integral of the unit step function, right? So if we integrate 1 dt, we're going to get t. And since it only exists from 0 all the way out to infinity, it's going to look like t times u of t. So f of t is the integral of g of t dt. So our Laplace transform for our function f of t is the Laplace transform of the integral of g of t. And using the time integration property of the Laplace transform, that's going to look like 1 over s times g of s, or 1 over s multiplied by 1 over s, or simply 1 over s squared. So let's take this one step further. This one isn't explicitly on our table, but we're going to use it to figure things out. So let's say that f of t was equal to t squared u of t. I'm going to then say that g of t might be 2t times u of t. Because the integral of this expression should give me t squared, right? If I integrate 2t, I get t squared. Now, I'm going to play with this a little bit, okay? So what I'm going to do is I'm going to make this work using the time scaling property of the Laplace transform. And I'm going to say that g of t is the same thing as 2t times the the unit step function of 2t. Is it okay that I made this substitution? What does a unit step function of u of 2t look like? The exact same thing as u of t, because we were expanding the time axis, but it's already going out to infinity. So literally nothing changes whatsoever. It still transitions from 0 to 1 at t is equal to 0. So I've changed nothing whatsoever. I'm going to call this function g of 2t. Okay. Such that my original function could be expressed as the integral of g of 2t dt. So my Laplace transform of f of t is the same as the Laplace transform of the integral of g of 2t. And so now I'm going to apply my time integration property and my time scaling property, right? So my time integration property is where I get this factor of 1 over s. I'm going to open my brackets here, and now I'm going to put in my time scaling thing, right? So if I have a function of a times t, I have 1 over a capital F of s over a, right? Let me just write that pair down here. Actually, you can just look at it. It's literally on your sheet as the time scaling property. So in this case, a is 2. So I'm going to have 1 over 2 times, it should be g at this point, of s over 2, where g of s over 2, so this is going to look like 1 over s times 1/2. And now I'm going to use my relationship for t of ut, right? So that's going to look like 1 over s divided by 2 quantity squared. So when I expand all this stuff out, I'm going to have 2 squared divided by 2, which just looks like 2. And then I have s times s squared is going to be s cubed. So the Laplace transform of t squared u of t is 2 over s cubed. Okay. Let's do this process one more time. Let's say that f of t is t cubed u of t. I'm going to call g of t three t squared u of t. And I'm going to try to figure out a way to put this in the form that I could use the time scaling property again, so that we're effectively just repeating the same step. So how am I going to make this thing a function of 3t? Right? So this could look like 3t squared times u of 3t if I just put a factor of 1/3 out front, right? Because if I FOIL all that crap out, I'm going to wind up getting 3t squared times u of 3t, where u of 3t and u of t are the exact same thing. So I have it in a good form. I'm going to call this 1/3 of g of 3t. And so f of t is going to look like the integral of 1/3 g of 3t dt. Are you catching what I'm throwing thus far? Andy, you're shaking your head no. What do you mean? So let me explain my thought process here, okay? I have t cubed. What's the derivative of t cubed going to look like? 3t squared, right? The reason why I wanted 3t squared is because I just figured out what the Laplace transform of t squared was. So I'm trying to build off of stuff that I already know the Laplace transform of to get the Laplace transform of subsequent things, okay? So if I know that the derivative of t cubed is 3t squared, then I'm going to call g of t 3t squared so that I can treat this thing as the integral of something because I have an integral property that I can use. Just trying to avoid doing calculus because of that. So in order to put this of the form where I can use the time scaling property, I need to make it a function of 3t, right? So u of t and u of 3t literally represent the exact same thing because you can't stretch infinity. I have to put this factor of 1/3 out here because when I do 1/3 times 3t squared, this is going to get me 3t with just the t squared, right? Because 3t quantity squared is 9t squared, and I need to knock that back down to just 3. So I ask again, where am I losing it? There is no ut in the integral whatsoever because I'm not doing the integral. I'm using the time integration property of the Laplace transform. So an integral in the time domain is a multiplication by a factor of 1/s in the frequency domain. I'm not doing any integration. Once again, I'm quite bad at it. You guys have seen it, right? So I'm trying to use the properties of the Laplace transform to avoid doing any actual real calculus, right? So in our class meeting last Wednesday, we covered all of these properties and they're also literally on the table. If you look at your table for time integration, the integral of a function is 1/s times the Laplace transform of the function in the S domain. That's all that I'm doing right here. This 1/s is for my integral. And then this thing right here is my g of 2t, where I'm taking the Laplace transform of g of 2t using the time scaling property, which is literally the one on the table that is directly above the time integration. So if a is equal to 2, I would have 1/2 g of s over 2. So what u of t are you speaking of? This one, it's in here. This whole thing is g of 2t. Let me take it back one step previously where we first started doing these things, and this might be helpful to you, right? So u of t by itself is our function g of t here. So we're just taking the integral of g of t. So the Laplace transform of f of t is the same as the Laplace transform of the integral of g of t. And it doesn't matter what g of t is, just in this particular case, it happened to be u of t. Applying the time integration property of the Laplace transform, we are going to get 1/s times whatever the Laplace transform of this is, which is a known quantity that happens to be 1/s. That's the process that I'm doing. So when we're down here on this second one, this is 1/a using the time scaling property times the Laplace transform of this guy evaluated at s over 2, because that's how the times stretching, what's the right word for it? Time scaling property works, right? So this 1/s squared bit, or excuse me, 1/s over 2 bit comes from the fact that we are looking at another way to kind of think about this. This might help you. If we let z equal to 2t, this would just look like z u of z, right? The Laplace transform of z, u of z, is 1 over s squared from our previous step. Going backwards, adding that scaling factor in is going to give us a factor of 1/2 here, and it's going to look like s over 2 here. So that's how we're doing this. Okay. So for this guy, my Laplace transform is going to be the Laplace transform of the integral of 1/3 g of 3t dt, which would look like 1/3 the Laplace transform of the integral of g of 3t dt. So that's going to be 1/3 times 1 over s times 1 over 3 times g of s over 3. Or 1/3 times 1 over s times 1/3 times 2 over s over 3 cubed. Where I used the Laplace transform of t squared to figure out what was going to go on down here. Boiling this big thing out, right? So we have a factor of 3 cubed in the numerator because we have s over 3 cubed in the denominator. So that's going to put a 3 cubed in the numerator. And then we have a 3 squared in the denominator. So we're just going to have a factor of 3, right? So this is going to look like 3 times 2. And then I have an s times an s cubed. It looks like s to the 4th power. Which would look like 6 over s to the 4th. But the more interesting way to look at it is this guy right here, right? So let's look at these 3 pieces together and see if we can figure out a path, okay? Sorry, what? Nailed it, okay? So up here, we have 1 over s squared. So the Laplace transform of t to the 1st power u of t was 1 over s to the, let's call it n plus 1, where n is the power on the time thing, right? If we go down to t squared, we have 2. So we can think of this 2 as 2 times 1, or 2 factorial, divided by s to the n plus 1. When we get to t cubed, we have 3 times 2 times 1, which is 3 factorial, over s to the 3 plus 1. So in general, then, for, sorry, I really don't like that color. F of t is equal to t to the n u of t. Its Laplace transform will be f of s is equal to n factorial divided by s to the n plus 1. And we prove that thing, which is rather difficult to do using integrals, just using the time scaling and the integration property of the Laplace transform. So we found out something that's really hard to do with calculus fairly easily using the Laplace transform properties, which is kind of why I want you guys to understand how to utilize the Laplace transform properties. So now let's look at f of t is equal to t to the n e to the negative at u of t, right? So how can we express this as something we already know the Laplace transform of? Well, g of t could be expressed as t to the n u of t, making f of t e to the negative at g of t. You guys catching what I'm throwing thus far? Hopefully fairly simple substitution here. Whenever we have e to the negative at times a function, that means we get to use the time shifting property of the Laplace transform, right? So the Laplace transform of f of t is going to be the Laplace transform of e to the negative at g of t, which is just going to be g at s plus a or n factorial over s plus a factorial. Sorry, I said time shifting, I meant frequency shifting. My apologies there. Frequency shifting property of Laplace transform. No integration at all in this one. So to do this derivation, I simply use the fact that I know the Laplace transform of this thing, and my function f of t here is just this thing multiplied by a factor of e to the negative at. Looking at the frequency shifting property of the Laplace transform allows me to split this into e to the negative at times a function that I know the Laplace transform of, writer. To the n plus one, sorry, not factorial. Yep, that's just me being a jackass. You're absolutely right. N plus one there. Is that what all of you guys' hands were about? Thank you. Yes. Yeah, thank you for that. All right. So the last one, so let's see. So we did we know what the transform is for number 1 on the table. We know what the transform is for number 3 on the table, also number 4. We didn't do number 6, but we can figure out number 6 from this one anyway, because n is just equal to 1 here. So that one's easy enough to do. We just did number 7. Let's look at number 14 very briefly, and then 15 is literally the exact same thing as 14, but from a different perspective. So we're going to have to wait on figuring out partial fraction expansion a little bit to figure out how that one's going to work. Okay. So the last one of these Laplace transform pairs that we are going to derive today is for f of t is equal to e to the negative at cosine omega t plus a phase angle times u of t. And we're going to do the exact same thing for this one as we just did for the previous example, right? So the function that I know the Laplace transform of is cosine omega t plus some phase angle u of t. And that allows me to express my original function as e to the negative at times g of t. The Laplace transform of my function f of t is the Laplace transform of e to the negative at g of t which we know to be G evaluated at S plus A. And so using the table here, we would just take our Laplace transform number 10, and everywhere we see S, we would replace it with S plus A, right? So that'll be S plus A sine theta minus omega cosine theta divided by S plus A squared plus omega squared. And that is a huge pain in the ass to do using calculus. All right, so like I said, there's two last things on the table, but we're going to table those things until we cover the partial fraction expansion of it. All right, so based on how much time we have left here, we'll probably only be able to do partial fraction expansion for distinct real poles, which you guys may not entirely know what the hell that means, so we need to introduce that too. All right, so this next portion of the class effectively is going to be dealing with largely the inverse Laplace transform, right? So up to this point, the overwhelming majority of the work that we have been doing is figuring out what the Laplace transform of any particular function is, right? Now that we have these transform pairs, we should be able to go backwards and figure out what the inverse Laplace transform of any particular function in the S domain is, okay? So for example, if I had the following function, f of s is equal to 4 over s plus 2 plus 6 over s plus 5 squared plus 8 over s squared plus 4s plus 5. And I want to find f of t, what would I do? So there's no need to do partial fraction expansion here. We already have the sum of a bunch of fractions, right? So let's just talk about baseline easiest case scenario. We have the algebraic sum of a bunch of functions that we know the inverse transform of, or can figure out the inverse transform of, right? So we might call this f1 of s, f2 of s, and f3 of s, and I would argue that we should be able to find the inverse Laplace transform of all three of these things, right? So the inverse Laplace transform of f1 of s would be the inverse Laplace transform of 4 over s plus 2, or 4 times the inverse Laplace transform of 1 over s plus 2. And what's the inverse Laplace transform of 1 over s plus 2? Use your table. E to the negative 2t u of t, right? So this would be 4 e to the negative 2t u of t. So that's our first part. Everybody catching what I'm throwing here? All right. What's the inverse Laplace transform of f2 of t going to look like? So this would be the inverse Laplace transform of 6 over s plus 5 quantity squared, or 6 times the Laplace transform of 1 over s plus 5 quantity squared. So using the table, what is this one going to look? There we go. T, e to the negative 5t. Right? So recall that tu of t was 1 over s squared, and then we just have that thing frequency shifted, which is where the s plus a bit would come from. Right? And again, this is one of the things that we put on the table today. So it's not super crazy that you guys didn't get it right from the jump. But does this make sense? If you were to do the Laplace transform of this, would you get 6 times that all day, every day, based on what we know? F3 here is going to be a little bit more difficult. Because in its present state, it's not really in the form that we know anything about. So we're going to have to get creative. So we would have 8 over s squared plus 4s plus 5. This isn't intuitively obvious, and probably not something that many of you guys have done since either your pre-calculus class or maybe, I don't know, the 8th grade. But s squared plus 4s plus 5 is really close to s squared plus 4s plus 4 plus 1. And s squared plus 4s plus 4 is something that we can factor and make it look like something we know how to do, right? So this would be the Laplace transform of 8 divided by s squared plus 4s plus 4 quantity plus 1. And I'm going to come down here. That would be 8 times the the inverse Laplace transform of 1 over s plus 2 squared plus 1. And I waited to take that 8 out until just now, because if you look at your table, we need something where this number in the numerator and this number in the denominator are the same thing. So which identity is that one? Absolutely right. So it's a sine function multiplied by e to the negative at, right? So this would be 8 sine t, or let me do it the other way around. E to the negative 2t sine t u of t. Putting all of these results together, the inverse Laplace transform of f of s would be 4e to the negative 2t plus 6t e to the negative 5t plus 8e to the negative 2t sine of t, all of this multiplied by a unit step function. Guys probably won't believe me here, but this is as easy as it gets. So our best case scenario, let me repeat that. Our best case scenario is our function in the S domain is split up into a series of functions that we know the Laplace transform of. This is the partial fraction expansion or partial fraction decomposition, use either word you choose, of a polynomial. Okay, so what I mean by that specifically, well, we'll talk about it here. Partial fraction expansion. In general, f of s could be written of the form s to the m plus some constant value, let's call it k1, s to the m minus 1, plus some other constant value, k2, times s to the m minus 2, plus all the way out to k to the m times s to the 0, where that would literally just mean we have a constant term with no s value at the end, divided by s to the n plus some other constant. Let's call this, I don't know, u. Where we have a polynomial as a function of s that I'm going to call n of s for the numerator, divided by a polynomial that is a function of s that I'm going to call d of s because it's the denominator, where, generally speaking, n is greater than n. Meaning that the order of the denominator needs to be larger than the order of the numerator. Okay? If that isn't the case, we have to start by doing synthetic division in order to get a polynomial of this form, which is a pain in the ass on top of an additional pain in the ass. So I'm not going to make you guys have to do that, but that's how you would take that into account, right? So not going to make you do synthetic division or anything like that. This will be annoying enough, believe me. All right. So we need to figure out a way by which to split this ratio of polynomials into a sum of smaller parts that we know the inverse Laplace transform of, and that would be a partial fraction expansion representation. So effectively, let's say that we have a function. What the hell just happened? Oh, wait, okay, there it is. Gently move it out of the way. All right. So let's say, and we're going to start with the easiest of these cases when we have distinct real poles. Okay. So let's say that we have a S domain function f of s that is equal to s squared minus 4s plus 3 divided by s cubed plus 4s squared plus 3s, like so. Okay. So first thing, is the order of the denominator larger than the order of the numerator? Yes. Order here is 3, order here is 2. We're in arguably good shape from the jump. No fancy pants math on top of other fancy pants math to be done here. Can either of these polynomials be factored? I think both of them can. Let's start with the one in the numerator, right? So if I have s squared minus 4s plus 3, what can I factor that into? S minus 1 times s minus 3, right? Okay, and if you can't remember how to do that in your head, your calculator can literally solve the second order polynomial for you and tell you what the roots are. So in the numerator here, we have s minus 1 times s minus 3. I agree with that wholeheartedly. All right. In our denominator, I think it's fairly obvious that there's a factor of s by itself, right? Because all of these terms have an s in there, so we can take that way out. Can I factor s squared plus 4s plus 3? S plus 1 times s plus 3, okay? Do any of these terms in the numerator cancel with any of these terms in the denominator? Unfortunately, no. So that means that what we are going to have to do here is we're going to have some number a1 divided by s plus some number a2 divided by s plus 1 plus some number a3 divided by s plus 3. So we are going to decompose our ratio of polynomials into a series of functions that we know the inverse Laplace transform. Okay? So these things in the numerator, a1, a2, and a3, have a special name. These are what are called our expansion coefficients. And these things in the denominator also have a fancy name. They are what are called our pole factors. Okay, so let's talk about what a pole means here really quickly. Okay, because we're going to revisit this topic. I can touch on it very briefly right here. But one of the next things that we're going to talk about in this class is using the Laplace domain transformations of signals or systems in order to look at the frequency response of that system. And having a polynomial like this is a fantastic thing because in our numerator is what gives us where our zeros are going to be, and in our denominator is what's going to give us where our poles are. Okay, so a zero simply means what value of s causes our whole transfer function to have a value of 0, and a pole is what value of s causes our transfer function to have a value of infinity. So our zeros in this case would be +1 and +3, and our poles in this case would be 0, -1, and -3. Because whenever something in the denominator goes to 0, the magnitude of the thing blows up to infinity, right? So our poles are defined by the polynomial in the denominator. Our zeros are defined by the polynomial in the numerator. We're going to use this in circuits 1. We're going to use it in electronics, electronics 2, all your controls classes, all this kind of stuff. Knowing where your poles and zeros are located. And guess what? They can be complex numbers. Will determine lots of different things like system stability and all kinds of good stuff like that. Okay. So a very important concept. We're just touching on things right now. Okay. So we have our expansion coefficients on top. We have our pole factors on bottom. All right. We need to solve for A1, A2, and A3. And these should be numbers. Once again, they might be complex numbers, but they're just going to be numbers. In this case, we have distinct real poles. Okay. So what do I mean by that? None of our poles are repeated because none of these factors are squared or cubed or anything like that, right? So that means all of them are distinct because none of them are repeated, and they're real because the value that causes these to go to each of these fractions to go to infinity is a real number, okay? 0 is a real number, -1 is a real number, -3 is a real number. So we have distinct real poles. This is the easiest case for partial fraction expansion. Then once we figure out how this works, next class meeting, we'll talk about repeated real poles, and then complex conjugate poles, and then repeated complex conjugate poles, and then we've covered every possible combination that we can have. So how we are going to determine the values of these expansion coefficients is by employing what's called the residue method, okay? So in the residue method, all we do is we multiply our function f of s by a pole factor and then evaluate it at the s value of the pole, okay? So for this particular example, we would find A1 is going to be S times our function f of s evaluated at s equals to 0, okay? So that means that we would have s times s minus 1 over s minus 3 divided by s times s plus 1 over s plus 3 evaluated at s is equal to 0. Very obviously, we can see that these guys cancel each other out. At s is equal to 0, we are going to have -1 times -3 over +1 times +3, and this comes out to be 1. So this is the value of our expansion coefficient A1. You got Brody and oh, well, I don't know what they taught you in your math class because I haven't taken math 245 in 17 years at this point. Yes, I'm not even going to keep letting you go on. Screw that. That sounds terrible. This is the ticket. Now, our process will change if we have different types of poles and all that kind of stuff. We'll wind up doing derivatives and things like that, but it's largely going to be this, okay? So, since you guys seem to like this version significantly better, which is great because it's easy, how am I going to find A2? S plus 1 times f of s evaluated at s is equal to 0. So that's going to be s plus 1 times s minus 1 times s minus 3 divided by s plus 1 times s plus 3 evaluated at, evaluated, it shouldn't be at s is equal to 0. What should it be at? -1, exactly right, because we need to use our pole value here. So s equals -1. Now I see why you guys were talking about dreading this, because it sounds like you were doing it in a brutally difficult way. Cancel this out, and I missed the s. Is that why your hand is up? Thank you, North. Definitely missed it. So, -1 minus 1 is -2. -1 minus 3 is -4. S is just -1. -1 plus 3 is +2. And so this is going to look like -4. And then our last one that we're going to solve for, A3, would be s plus 3 times f of s evaluated at s is equal to -3. So that's going to look like s plus 3 times s minus 1 over s minus 3 divided by S times S plus 1, S plus 3. This guy and this guy cancel. We are evaluating it at S is equal to -3. So -3 minus 1 is -4. -3 minus 3 is -6. -3 by itself. -3 plus 1 is -2. So 24 over 6 is +4. Putting all of this together, f of s would then be 1 over s minus 4 over s plus 1 plus 4 over s plus 3. And so f of t would be 1 minus 4e to the negative t plus 4e to the negative 3t u of t. All right, so we ran out of time. So couple of things. Once again, I want to reiterate, we're not going to be able to have class on Friday because I have other obligations with the Industrial Advisory Board meeting. You all are invited to attend the project pitch presentation as well as the workshop on Friday afternoon. I have several lecture videos that I need to get uploaded for you guys. So I'll work on doing that probably tomorrow, but it could be as late as Saturday, just depending on how busy I get with other crap. I'm going to put a homework assignment up, and I'm going to tentatively put the due date for next Wednesday. The homework assignment is just going to be, one problem will be find the Laplace transform of various functions, and then the second problem will be find the inverse Laplace transform of various functions. And the reason why I'm saying the tentative due date is next Wednesday is because I believe we will cover all of the partial fraction expansions for other cases by the end of next Monday's class meeting. But if we don't, I will obviously have to push the homework due date back so that we have time to cover all the material. So the next, yeah, so I think that's all that I wanted to talk about. Yes, sir.
Was the in-class and statement portion of the exam related?
So the in-class portion of the exam is worth 75 points. The take-home portion of the exam is worth, I think I have it as 30 points, so there's 5 points of bonus built in.